This year, World Space Week has been celebrated with the theme of living in space. When we discuss living in space, the question is not just how to get there, but how to stay there for long periods in a safe, efficient, and sustainable way. Traditional model of human habitation has relied on rigid metallic modules, which are structures designed to resist pressure from within and protect against a vacuum from outside. This design approach works well for short-term missions or small-scale stations. However, as we begin planning long duration missions and permanent bases beyond Earth, rigid structures face a very clear limitation. They cannot be scaled easily with the current launch vehicle constraints. This is where inflatable or expandable habitats, as they're being known as, become important. These structures fundamentally change how we can design for human spaceflight. Instead of manufacturing large, rigid shells on Earth, which are limited by the size of the rocket fairing, engineers can build compact, flexible systems that can be folded or stacked up, launched efficiently, and then expanded once they reach orbit or a different planetary surface. The advantage is immediately measurable. It offers a much higher ratio of usable internal habitable volume to launch mass. The core idea is based on efficient use of pressure and materials. A rigid structure must resist internal pressure through stiffness and mass. An inflatable structure uses internal pressure as its main source of strength. Once deployed and pressurized, the tension created in the restraint layers maintains the shape and rigidity. This allows engineers to achieve structural stability without adding unnecessary layers of mass, which is one of the central goals in space systems design. An inflatable habitat is a complex multi layered system made from advanced flexible composites. The innermost layer is usually a gas retention bladder that ensures that the internal atmosphere remains sealed. Outside of this, there is a restraint layer made from high strength fibers, which carries the load generated by internal pressure. The outermost layers provide protection from micrometeoroid impacts, space radiation, and thermal cycling. Together, these layers can create a system that is both flexible and mechanically strong under pressure. Before deployment, the structure is packed and mounted inside the launch vehicle's fairing. The fairing is the structure that provides aerodynamic protection during ascent of a rocket and shields the folded habitat or any other payload for that matter from acoustic and vibrational loads. Once in orbit, the upper stage performs the final orbit insertion, and after required checks, the fairing is jettisoned. Inflation then can begin in controlled stages. If they're using a gas, depending on the system, maybe nitrogen or oxygen, it can be introduced slowly to expand the structure. There are sensors that have to be installed at different places to measure strain, temperature, and internal pressure. The process can take several hours, as any uneven expansion could create stress concentrations or damage the restraint layer. Once fully inflated, the structure can transform into a rigidized pressure vessel. The internal pressure, which is around 1 atmosphere because humans are going to live inside, is enough to keep the habitat stable, while the restraint layers can prevent overexpansion. The result will be a habitable volume that can be multiple times larger than what was initially launched. This scalability makes inflatable habitats particularly attractive for space stations, lunar bases, and deep space missions where crew comfort, workspace, and redundancy are going to be very, very important. From a structural standpoint, the pressure load acts uniformly across the surface. The restraint layer converts this load into tension, which is distributed evenly. Unlike metallic modules that experience bending or localized stresses, inflatable systems operate primarily under tension, which is a condition that materials like woven composites handle very efficiently. Engineers test this behavior extensively on the ground using vacuum chambers, pressurization rigs, or environmental test beds. These are the tests that can simulate years of cyclic loading to evaluate for fatigue, material degradation, etc. Thermal control becomes obviously a critical subsystem in this one. Flexible materials do not always conduct heat effectively, so inflatable habitats require integrated multi layer insulation and active thermal management systems. Radiation protection is addressed through layering and material selection. While flexible composites cannot always match the amount of shielding capacity of aluminium or titanium, they can incorporate radiation attenuating materials such as polyethylene or hydrogen rich polymers. These are the materials that are effective against galactic cosmic rays and solar particle events. For long term missions, inflatable habitats can also be combined with external shielding, for example, by covering them with lunar regolith or Martian lava tubes. Micrometeoroid and debris protection relies on the Whipple shield principle, where the outermost layers act as sacrificial bumpers, fragmenting incoming particles before they can penetrate the inner pressure layers. Each impact is absorbed through multiple layers of energy dispersion. These design strategies are being tested under hypervelocity impact experiments, confirming that multi-layer composites can achieve protection that may be comparable to metallic walls of much greater mass. The interior of an inflatable habitat is equipped with life support, power, and other environmental systems, much like any crewed spacecraft. The flexible nature of the walls allows modular reconfiguration. Internal panels, lighting, and system racks can be repositioned as mission requirements evolve for human spaceflight. From a systems engineering perspective, inflatable habitats offer some significant logistical advantages. They reduce launch volume, simplify some levels of integration, and can enable modular assembly in orbit or on another planetary surface. Multiple units can then be interconnected using docking adapters, creating expandable stations or surface bases. This modularity aligns with the long term goal of scalable space infrastructure, that these are systems that can evolve without full redesign. The main challenges for inflatable habitats are stacking, pressure control, long term durability, maintenance, among many others. Continuous exposure to vacuum space radiation can gradually degrade polymers and coatings. Advances in additive manufacturing could eventually allow on site repair or reinforcement using materials derived from local sources. Psychological and operational considerations are also significant. Larger habitable volumes improve crew comfort and mental health. The ability to move, to designate private areas, and to maintain structured work and rest environments directly affect performance during missions lasting months or years. Inflatable habitats make such spatial design possible without the mass penalty of rigid architecture. There are already several organizations around the world building and testing these inflatable space habitats. Let me know in the comments if you know any one of them, and stay subscribed to this channel for more videos on spaceflight.